Okay, so the differentiation that you know from C3, you're on C2 and C1 in fact, you're going to be using in reverse to find integrals. First of all, I'm just going to do the basic integrals that you need to know from the differentiations that we already know. Okay, so the first ones, if we start with, if we differentiate x to the n, we get x to the n minus 1. So what about if we want to integrate x to the n? Okay, with respect to x, then the opposite, when we differentiated, we subtracted 1 from the power, so we're going to add 1 to the power, and then when we differentiate, we're going to multiply by that n plus 1, but we don't want it, we haven't got an n plus 1 at the beginning of the integral, so we'll have to divide by it instead. So the integral of x to the n is x to the n plus 1 divided by n plus 1 plus c. If we differentiate e to the x, we get e to the x, so if we integrate e to the x, we'll just get e to the x plus c. If we differentiate ln x, we get 1 over x, so if we integrate 1 over x, we'll get ln x plus c. So that looks quite straightforward, but we can also use those with the chain rule, so let's make some slightly more difficult examples. So let's say, okay, what about if we've got, well, this one isn't more difficult, it's just an example really. Let's say we've got 4x to the power of 5 and we want to integrate that. So we will add 1 to the power, which is 6, and then we've got to divide by the 6, but we've also got a 4 at the front there, so we end up with 2/3 x to the 6 plus c. And it's always a good idea to just, in your head, differentiate again, so 6 times 2 will be 12, 12 divided by 3 will give us the 4, and the power of x would reduce by 1, so we'd get x to the 5, so that's okay. What about if we've got the integral of e to the 2x minus 3? Okay, so we know that basically it's going to be e to the 2x minus 3, but then if we differentiated e to the 2x minus 3, we'd have a 2 at the front because we have to differentiate the power that e is raised to, so when we integrate we do the opposite of that and divide by 2. So it's 1/2 e to the 2x minus 3 plus c. Okay, what about the integral of 1 over 4x minus 7? Okay, so our first guess at that would be the ln of 4x minus 7, because we know when we integrate 1 over something, we get ln of that thing. But if we differentiated ln of 4x minus 7, we'd have the 4x minus 7 on the bottom, but we'd have the differential of 4x minus 7 on the top, which is 4. So we don't want that, so we just divide by the 4 instead. Okay. Right, so those are some of your building blocks for integration. The others are all to do with trig. So a useful reminder of our differentials. So if you differentiate sine x, you get cos x you get minus sine x. And if you remember, we did those in a little sort of circle. So going around in this direction, you get your differentials. And if you go in the opposite direction, you'll get your integrals. So that's a useful way to remember your integrals and differentials of sine and cosine. So, for example, if we want to integrate sine of x with respect to x, sine of x integrates to minus cosine of x plus c. So a little bit more complicated if we've got the sine of x plus pi, say. We want to integrate that with respect to x. We're going to have minus the cosine of x plus pi. And then if we differentiated that, we'd have to multiply by the derivative of the brackets, which is only 1 in this case. So we'd have minus the cosine of x plus pi plus c. Okay, so integral of cosine of x dx is just the sine of x plus c. So the integral of, let's say, 4 cosine of 2x minus 1. Okay, so we know it's going to be something to do with 4 sine of 2x plus minus 1. And if we were to differentiate that, we'd have to multiply by the differential of 2x minus 1. So we need to divide by that, which is 2. So we just end up with 2 sine of 2x minus 1 plus c. Okay, let's make a bit of space for a sec squared one. So when we differentiated tan, we got sec squared. So if we integrate sec squared of x, then we will get tan x plus c. So if we've got the integral of sec squared, let's have minus sec squared 3x minus 1. Okay, so our first guess would be that it's going to be tan of 3x minus 1. If we were differentiating that, we'd get a 3 at the front that we don't want. We've also got a minus that we don't, that we just leave as it is. So we've got minus a third of tan of 3x minus 1 plus c. Okay, so our remaining three trig differentials, cot cosec squared, sec differentiated to sec x tan x, and cosec x is minus cosec x cot x. So the reverse of those, so if we want to integrate cosec squared of x, then we're going to have minus cot x as our answer. So if we're going to integrate, say, 8 cosec squared of 2x with respect to x, then we're going to have minus, because when we integrate cosec squared we get minus cot, we'll have an 8 there, cot of 2x, but then we would have, if we were differentiating, we'd have to multiply by 2, so when we're integrating we divide by 2, so we've got minus 4 cot of 2x plus c. So the integral of sec x tan x is sec x plus c. So the integral of, let's just have sec 3x tan 3x will be sec of 3x, and then if we differentiated that by the chain rule, we'd have to multiply by 3. So this time, because we're integrating, we need to divide by 3. So a third of sec 3x plus c. Okay, and for completeness, let's have the integral of cosec x cot x dx is going to be minus cosec x plus c. So an example of one of those. So we've got cosec of 2x minus 1 cot of 2x minus 1. Okay, so we'd expect it to be minus the cosec of 2x minus 1. But if we were to differentiate that from the chain rule, we'd get a 2 at the front, which we don't want, so we'll make it minus a half cosec of 2x minus 1 plus c. Okay, and basically from these 9 integrals, using them in conjunction with the rules for integration that you're going to learn as we continue through, you'll have everything you need, hopefully.